Okay, so I'm going to start because tonight we are going to have a longer session because a lot of contents to cover within a short time because it's the week 4 and we are going to talk about some key concepts related to statistics, which is our inferential statistics, and specifically we will see some of the inference hypothesis testing. So we'll walk you through that. So agenda tonight is my share file. This is the file. Okay. So I'm going to cover this thing as a 2 sessions. I will explain the theory first, walk you through the theory so that you can understand the content. So it's expected that you go through the lesson contents and you do the examples by yourself using R. So I'm not going to repeat those example as it is. Rather, I will pick a different example, a different data set to explain the tests, explain the concept, but you should do your self-test, like a self lesson to run those code that is given in the slide, in the lecture notes. So, and you run that by yourself and see if it works. So, so that's why I have session which is walk you through the same concepts, same different tests with different data set, and R session. But before I go there, I will explain the contents so that you, when you read that, you can understand it in a sensible way. So I will recap. First is about the central limit theorem, because as I said before, it's one of the key concepts about our inferential statistics. So we assume something, and that based on the assumption, our hypothesis and our all statistical formula has been developed, and this is the concept. So I repeat again, this is the concept of central limit theorem, that if you choose many iterations of simple random samples from a population, the mean of the sample, okay, the distribution of the means of the samples, if you eventually plot that, if the sample size is large enough, and then it falls in a standard normal curve. But if the sample is small, then eventually it will do a normal curve, but then we call that a t-distribution, that we will see later. So the idea is that in the picture, you can see that you can have different kind of population distribution. The population, the figure in original, the name original is, you can have a distribution like that. You can distribution have a skewed or like a very irregular distribution of population data. But if you try to take a sample, a simple random sample from the population, and if you keep on iterating the samples many times, and as the sample size increases, you eventually see a bell-shaped curve. So whatever the population is looking like, but your simple random distributions and mean distribution of the sample distribution will eventually end up with a normal, like a bell-shaped curve. Okay, that's the idea of like central limit theorem. So that means the mean is concentrated. The peak is basically is indicating the mean, and all other varies are like as a centraling, are going to the center of the mean. So we don't have much dispersion. Eventually, if our sample size is bigger, and then if we do it many times, then it will be like a peak. So you will not a long tail, it will be like a highest peak. But if our sample size is small, then we have a fatter tail, which is eventually our t-distribution. So from this, we understand that the larger the sample, the more normal the distribution. So if you have eventually bigger samples, our distribution tends to be more normal. And the more samples, the more normal will be the distribution of all the means from all those samples. So as you can see, like whatever the population is looking like, but our sample, eventually if we get the mean of the sample, it will be eventually fall into a normal curve. So we understand that, and having that in mind, just keep this knowledge in mind, because then we will use some of the formula around this central limit theorem. So now this gives us a kind of idea what we are trying to achieve, and you have just completed your like a design of an experiment and how that fit into the whole journey. So think is like you think about a population. So in a statistical domain, we probably not deal with the population as a whole. Okay, we take some data from the population through random sampling. Okay, that's called sample. So there are different techniques of sampling. Yeah, and the best technique and the ideal technique is simple random sample. And we take a sample from the population. That's our data basically. Okay, so in your experimental design, probably you have thought about collecting a data. So that was a plan, how you want to collect the data. So, and then once your data is collected, either you can represent that whole data as your own population, and then if that is a population, and then you have to use simple random sample to get a sample from your population. So eventually, you get a data, and then which is like a subset from your population. And on that data, we run statistics, okay? And there are the statistics of mean, median, and whatever we try to do in terms of testing. So that is a statistics, and it basically tries to infer some parameters, like it tries to estimate or predict or like evaluate or try to guess the parameter of the population, the characteristics of the population from the sample. It's like we try to infer the mean, for example, of the population. If we take the whole, because we don't collect the data from each and every one, but we take a random sample from the big population, probably from a suburb or from multiple suburbs, and then we try to infer the whole, the median age or average age of the population, okay, through statistics. And then we try to also tell that, okay, how significant our guess is, how confident our guess is. So these are the terms we use when we try to infer, and so that people understand like there's chances of error, what is our like the chances of error, and what is our confidence level. So these statistical terms or jargons are used when we do inferential statistics. So now week 4 is talking about inferential statistics, okay? So in this case, we will be dealing with a sample, simple random sample, to infer some of the parameter. In this case, our parameter is mean and variance, because we are doing 2 tests today, which is our t-test and ANOVA. So t-test is a test of samples. So we'll see different kinds of t-tests, and basically it's testing across the mean. And we have ANOVA, which you can, from the name itself, is analysis of variance. So these are the 2 parameters. That's why it's called parametric test. So we have a sample representative of a population, and we know those values as parameters, which are the mean and variance, and we try to infer the mean and variance of the population, okay, from the sample. So this is all about our statistical tests. So now, if you can, I'll like explain a few concepts about the statistics. So we have a Z distribution or Z statistics that comes from the Z distribution, and we have the T distribution, and we call the T statistics. So the basic difference between Z and T is number of samples. Okay, if our sample size is increased, like bigger, we fall into the Z statistics measure, like it's a normal, like a standard normal curve. And if our sample size is small, probably we can safely guess, or we don't know the sigma or the standard deviation. So we ultimately it goes to a t-test, but it's eventually a similar like a normal curve. So so before we go there, let's see how it works. Okay, what's the formula? What's the theory behind it, and why we use it? So imagine we have a sample, simple random sample of like the size of sample is n, and the n could be like a small or big. Okay, at this case. So if as I said, if it's a small n is bigger, then it falls into Z statistics. If n is smaller, then it falls into T statistics. So now we take a sample of size n, and from the sample we can calculate the mean. So we know the formula of mean, which is x bar, that represents the observed mean from the sample. Okay, this is called sampled mean. Then if we have, now from the central limit theorem, we could probably get many samples and many and that eventually give us a sampling distribution. So definitely the sampling distribution should have a mean, and we call that mean as a like assumed mean, or you can say sampling distribution of sample mean. Okay, that means is the mean of the samples, and if we take multiple samples, that's the mean we have, which is our assumed mean. Now, if we plot this, it will become a normal curve, right, from the central limit theorem. And we know the standard deviation of sampling distribution, or like we know the standard error, like we know the formula of a standard error of the mean, and we know that. Okay, so from the lecture 1, we know how to calculate the standard error. Now, if we know in the graph, so if we know the assumed mean and we take a sample, which is a sampled mean, or the observed mean, which is x bar. Now we want to say how far or how close it is from our observed mean. Okay, so it gives us a kind of a distance from a standard like a manner. So that's called the z distance. Okay, so if you can see the picture, like I said, this gives us a kind of idea how far our observed mean is from our assumed mean. Okay, and then if in this case, because we are working with the sample, if the sample is bigger, then the distance is calculated from the z distribution that we call z statistics, and if our sample is a small, which is less than 30, then it becomes a t statistics. Then we take the t statistics. Okay, so and the formula is like that. So it's just calculating the number of standard deviations, a number of error, like a number of in this case number of what's that standard error away from our sampled mean, from our assumed mean. So x bar is our observed mean, and mu bar, which is our like a assumed mean. So we want to calculate the distance, this, and this give us that statistics. Okay, this is called the statistics. Okay, so our statistics, and given this value, either is coming from a t distribution or z distribution, then we use that value, which is the statistics value, to do some other stuff that we will be seeing later. Like we use that to calculate our confidence interval. We use to test our hypothesis based on that. So we'll see that. But the whole point is, given a like a sample and knowing the distribution, we will be able to understand how far or how close that observed mean is comparing to our like assumed mean. Okay. Now, so this is the slide for the t distributions, just to give you an idea. Like as I said before, a t distribution is is nothing exceptional than the z distribution or a normal distribution, but only difference is it is not actually it is for the less number of n observations. So the same how the distribution is calculated. So like normal distribution, if the n is small, we take the random samples of multiple time and we calculate the probability, and that eventually give us as like a t distribution. Okay, so because we don't know the standard deviation of the population, so and that's why the important term in this case is the degree of freedom, which is the number of ways you can make the statistics. Okay, so the formula is the number of degree of freedom is the number of samples minus 1. Okay, and then the t distribution look like a normal distribution, but it is fatter in the tail. You can see that the degree of freedom is less, it has a more fatter tail. The degree of freedom, if the sample size increases, it eventually reaches to the standard normal distribution. So as I said, if if the n is greater than 30 or even like 100, it's almost like a normal distribution. Okay, and the x-axis is giving us a kind of a value, that the t value or z value as a distribution, but y is giving us the probability. So even at a given point, it gives the probability, and from that point to the upper to the tail, which is called the region. The regions give us the integrated the area under the curve give us the whole probability as an integral value. Okay, so we have a probability point, and from that point to up onto the left tail or right tail is give us the whole probabilistic measure. So y scale is giving us the probability, and x is giving us a particular value, like either so that gives us like how many standard deviation away, or how many based on the degree of freedom, how many t star or like a t value away from their like assumed mean. Okay. Now, as I said before, so it is actually kind of it's not dependent of any sample, and that's why if we have a known value for given a degree of freedom. So there is a table. You can look at Wikipedia or many other sources. If you Google like the t distribution values, and you will get a table which just give us a kind of a like a, you know, there are two one tail, like a two-sided or one-sided, and we have a different level of significance that we will see what is the significance level, that is our margin of error, and also the degree of freedom. So like how many degrees of freedom. So given the degree of freedom, we have a specific t value in x-axis. In x-axis, as I said, so we know the value, and from that point, if we look at the y-axis, we get the probability as like a shaded portion. So that gives us the probabilistic distribution of the t distribution. If we know the t value, we will be able to calculate the probability of from that point under that curve. Okay, so this is like a known value. So that's why given any sample, any random sample, we will eventually be able to calculate the t value. And using the t value, because t value is not dependent to our sample or any sample, it is actually a known distribution and known probability curve. And using that t value with that given degree of freedom, we'll be able to calculate the probability. It's just a lookup table. And this is the if you look at the table, then you will notice that as the degree of freedom increases, it reaches to the z distribution value. So given the degree of freedom 10, 20, 30, and like a z, so if you look, the t distribution reaches to the z distribution as the degree of freedom increases. So we know that as a theory. Now we try to solve the problem using this knowledge that we have got so far. So the question in this case is, in a school scenario, it's like a school is making a team of a programming team to be sent for a programming contest. So they're asking for the mean IQ of all the students going for a programming contest from a school needs to be above 100. Okay. So 10 students are selected by simple random sampling, and here is their IQ score. So we got an IQ score of like this of 10 students. Now the question is, does the data we given here have sufficient evidence to conclude that the sample meets the requirement of like they should have the 100 above 100 IQ? Assume that we are risking 1% of error, type 1 error. So we'll know what is type 1 error in the next slide. But the problem is we are trying to get a sample, and the sample should require above 100 IQ score. Okay, and this is our random sample. So from that, what we have got so far, we got a sample mean. We can calculate the sample mean as x bar. So from 90, 105, these values, and we got 104. And we can calculate the standard deviation from the sample, which is our S. Now what should be our null hypothesis? So before I go there, hypothesis, null hypothesis is always a hypothesis that you want to reject. Okay, and the hypothesis is the alternative hypothesis, or H1 is the hypothesis, is a research question, what you actually after. So in this case, how we can nullify our research question? Say the sample doesn't meet. So if you said the sample doesn't meet the requirement, that's the way we can tell. But how we can quantify it, how we can mathematically represent it. So if we say it just failed the requirement of the mean IQ is equals to 10, that means if the mean IQ is just equals to 10, then that means because it's asking for above 100, above 100. So if the mean IQ is just equals to 100, then it's failed, right? Our requirement doesn't meet. how our requirement could be met, which is our test hypothesis, obviously H1, and then it should be a IQ above 100. Okay, so and then we know that we'll see that also that we can reject the hypothesis. We will reject our null hypothesis if assuming that our hypothesis is true and our sample mean is this, like a conditional probability wise. So we are going to calculate a probability of finding the sample mean of 104, given that our hypothesis is true. Okay, and also our chances and the probability is less than 1%. Okay, the probability of having this have less than 1%. If it is the truth, then we can reject his hypothesis. Otherwise, we will accept the hypothesis. Okay, so having this, because it's a sample of tens, we can easily apply the t-test, like a t-score, like a t-statistics. So we can get a t-score from the formula above. In the previous slide, we calculate the t-value, so which is like 1.07. So from this 107, how we can get that value? So since we are actually finding the greater than, so it's just a one-sided test, because as you can see, the t-value, the t-distribution is symmetric, but it's just not like a one-sided, because it's just not equals to, it's not like not equal to, it's just checking whether it is above 100, 100. So we are just checking for one-sided test. Okay, so so we can see where it goes. So that's why we see from the table one-sided, we have to look up the value for one-sided, and we are after 99%, because 1% is our error. So 99% accuracy we want, 99% confidence we have. So that means we want to have 99% assurance or 99% probability. And then because the probability can go 100%, right? So we want to get 99% probability wise. And then degree of freedom in this case is a 10 minus 1 is a 9, and we get the value. Okay, this is the 2.82. So 2.82 is this value, but our value is 1.08. Okay, so now what does that mean? So it is actually here. So 2.18 is where we have put the red is this value, and this little dot, green, and the blue dot is actually our observed value, like our obtained value as a t-score. So it is just beyond the rejection region. So we'll see that what is the rejection region. So that means the probability, if the point is within this region, then we could reject the null hypothesis. But since it is not, because there is no because there are chances, because it is beyond the rejection region, so we cannot reject the hypothesis. That means there are many chances that this requirement will not be met. Okay, so from this sample we can conclude that from the given sample it doesn't meet the requirement of that requirement we are. So the sample doesn't meet the requirement of of this alternative hypothesis. So we cannot accept the alternative hypothesis. We just accept it. Okay, we just accept the null hypothesis in this case, because the sample doesn't meet the requirement. This is the conclusion we can make from that. So two-sided is if our condition is mean IQ is not equals to 100. So that means it could go either left side or right side. But here we are explicitly saying like it is greater than 100. Okay, so that's why we are getting one side of the test. Okay, so we will see that in your lecture note you have both cases. We are checking the not equals to, or you say either greater than or equal or less than. So and we'll see one of the slides I have explained, like how we can test what does the two-sided test mean. Okay, now the other important concept is confidence interval. So as you know, the thing before, like a Z statistics and T statistics, so that's basically our K value. So what does confidence interval mean? So if you can recall that picture, we are trying to estimate how precise your sample statistics, for example, mean, variance, whatever that parameter, we are trying to guess or estimate from the population. Okay, So it is actually a guess of our okay, so the 1.07 is actually, we got it right from the TS score is this. So this is our value. Our obtained value lies here, but where our confidence, where from the table we get the value here. Okay, so we could reject the hypothesis if our value is, if our dot is in the rejection region. Okay, but in this case we cannot reject the hypothesis because it is possible. Okay, so the hypothesis H1 is possible, H0 is possible. That means it failed the requirement in this case because our hypothesis is just failed. Yes, this is for one sample. Yeah, we are not going to the, we still are not going the t-test, but we are trying to understand the value. So t-test will give you more clarity. So we'll do the t-test in an example, but we're trying to understand the value from the table and trying to understand what does value mean on the distribution curve. Okay, so the y-axis is giving us a probability. So the probability of getting a point here. So the probability is higher. Okay, but if the point is here, then the probability would be low. So that means in this case we have a higher probability of having the hypothesis 0 being true. Okay, so that means we cannot reject this hypothesis as null hypothesis. We will accept the null hypothesis. So confidence interval, as I said, is like a estimate of your parameter from an observed sample, and this is the value. This is the like a common. You can think how we can calculate it. So if we can, there are two ways. As I said, if you can come with a Z statistics, or if you are in a T statistics, if the sample size is large, definitely we know the sigma, and if a sample is small, we have a like S. And then we go the T statistics, and otherwise we go the Z statistics, and from Z statistics we know the Z value, and T statistics we know the T value as I have shown, and then that basically becomes our K, and we know how to calculate our standard error. So the equation for the standard error is like our standard deviation due to our number of observation, our sample size. So this is the value. Okay, and X bar is our observed mean, like from the sample mean, and then plus minus give us the range. So if I just put an example, so a random sample of 30 households was selected as part of a study of electricity uses, and the number of kilowatt hour as recorded for each household in the sample for the March quarter of 2006. Okay, and we have the average uses, which is 375 kilowatt. In a very large study in the March quarter of the previous year, it was found that the standard deviation of the users was 81 kilowatt. And assuming the standard deviation is unchanged and the users is normally distributed, because there is always an assumption on the sticks of the parametric test, the data has to be normal, and provide an expression of calculating the 99% confidence, then we should see where our mean, okay, our mean uses, what is the confidence level we can have. Okay, so from this formula we can see that with the 99% confidence. Okay, so we have to calculate the Z value with the 99% confidence, and with the parameter 81 and the number of samples at n, we calculate from the Z distribution, we get the value for the Z of the probability of a Z becoming 0.99, which is the value is 2.58. From the, remember the region of the normal distribution, the 6690 that rule, and the 99% rule is giving the 99% probability is giving us 2.5 standard deviation. So that becomes the Z score in this case, and plus minus that give us a region, like a boundary. That means this value definitely with 99% confidence we say that the observed the population mean will fall between these two values. Okay, and we will see that in an R example with a practical data set. So confidence interval is giving us a kind of a range within which our like a parameter should fall with some confidence. And some of the definitions, probably you know the hypothesis and null hypothesis. So an alternative hypothesis, as I said before, alternative hypothesis is the claim or your main research questions, and null hypothesis is always against that. You think everything is normal, nothing is happening. But an alternative hypothesis, no, the treatment or the experiment you are doing is having an effect. So that is our alternative hypothesis. And so the hypothesis testing is basically we take a samples and then from the sample we try to guess how significant or you can like accept or reject the null hypothesis. This is basically the testing of their two hypotheses, how we can accept or whether you can reject, and we see how there are ways how we can do that. And the type of error is taking like considering the chance, okay, taking a chance of that you are, in the case of null hypothesis is true, but you are rejecting it. Okay, that is our type 1 error. But type 2 error is different, which is like your null hypothesis is false, but you are trying to accept it. So this is a type 2 error. But always we try to avoid the type 1 error, which is basically like biggest blunder. Okay, so now definition is test like you can see this is the generalized formula. If you can recall the previous slide, so you have a test statistics, either is it a z-score or t-score. It is basically that statistical value, which is basically observed value, in this case our observed mean minus hypothesized value, which was like distribution like a assumed mean divided by standard error. Okay, this is the generalized formula of our statistics, and we have z-score or t-score, and that becomes a statistics. So we know that, and we have seen that before. Now, knowing that, this becomes like because since this is a statistics, so we have different kind of distribution. So different kind of distribution will have different kind of statistics. Like we have a t distribution, we have z distribution, we have f distribution. So from those distribution, we get different statistics, and knowing our data, we will apply different function to get our value. And obviously, we will try to avoid avoid some of the errors. So that's why we risk some of the error, which is called like a risking of error, which is our significance level. So our significance levels is represented through alpha. Just it should be 1 alpha, and that means 0.05 means like we are taking 5% or 1% or 0.1% of error, like error. Okay, this is our significance level, and we pass that as a parameter to test. And the rejection region is graphically I have shown that. So rejection region is from the point you get your statistics, like a test statistics, and up until the whole the tail, the total tail gives us the rejection region. So, and then if our observed mean, our observed statistics fall within that the region, that means it's a rejection region. That means we can then reject our null hypothesis and accept alternative hypothesis. This is one way of rejecting or accepting a hypothesis. The other way is the p-value. Because the distribution not only give us a region but also give us a probability. As I said, like y-axis is our probability point. So if we know that probability, the p-value is less than our alpha, our significance level, then we can reject. And if a p-value is greater than alpha, it's a bigger, then we cannot reject. So in the example I just showed our not the p-value, I showed through the rejection region. So our rejection region, the point didn't fall in the rejection region, that's why we cannot reject it. Okay, but same thing we can do. Either we can accept, reject. We can see that through the p-value. So this is the flow diagram of significance testing, and it is from your lecture note, so probably you know that. So what we always do, and if you look at your examples step by step, what we did in every cases. So we got the data first, and we did some exploratory data analysis. For why? Because we want to confirm that data is normal. Because for the parametric test, we have an assumption the data is normal, and they have some like a standard like equal variance for the variance test. and then yeah, and then there should not be any outlier, because if the outlier, then it will be our results will be impacted. So we do some treatment on the outlier, we remove the outlier and recheck the data is normal. If data is not normal, or if data is not, then we probably transform the value so that it looks like normal. Okay, so we do some vision, like prepare our data set and do some visual exploratory analysis to meet the assumptions, and then we formulate our hypothesis as like a null hypothesis and alternative hypothesis. So our research question, which we are actually after, that is our alternative hypothesis, and which our research doesn't work, which is basically our null hypothesis. And then based on the number of n on observations or even the data, if you want to compare multiple means, multiple like a data set or many groups, we go ANOVA. If you have a two, or you have one pair, or if it's a dependent, we say a different kind of tests. We have a different kind of tests, the t-test and ANOVA in this week, but we will see many other tests. And these are parametric tests because from this distribution, we can calculate their mean and variance. That's why it's parametric test. And then we test our hypothesis in two ways. Either we can get the test statistics through the formula we just come across, and we get the either Z score or like a T star or Z star value, or even ANOVA, and then we can calculate the rejection region. Okay, and then we can understand whether it falls within where our observation falls, in the rejection region or outside the rejection region. Or we can calculate the probability, and based on the probability value, is a small or a greater, we can like accept or reject, and we interpret that. Okay, what if our assumption opposite? What does that mean? Like you mean the hypothesis? Yeah, so like yeah, opposite. No, it is actually, you know, what is a research question? That research question is your alternative hypothesis, and whatever is not your research question, against your research question, is your like a null hypothesis. So it's very contextual. So you can have a different questions, yeah, and from the same data set. So and that's why probably it's important to formulate the hypothesis question. Okay. And this small figure is showing us like a two-tailed test or one-tailed test where we should go. If you are trying to like your alternative hypothesis is two-sided, in it like is not greater than in the case of is not greater than, that means it could be less than or it could be greater than. Okay, is not equals to, then it is basically a two-sided. But if you say no, if it is greater than, then it's one-sided. If it's less than, then it is another-sided. So this is why we get a like a two-sided test or one-sided test. And two-sided test means we have to take the probability of both of the regions to get our aggregated probability. Okay, and that becomes our rejection or acceptance region. If the assumption is not from probability distribution, what do you mean by that? If the assumption is not from a probability distribution, I'm not sure. Like it has like the sample should represent a normal distribution. If it is a normal distribution, that means we know the parameter. It's a parametric test. If it is data is not normal, then definitely it is not a yes, it's a non-normal. Yeah, so you have to wait until we talk it about in the next week, where we have chi-square test and some other tests like Wilcoxon's test. So that's the different kind of test. Okay, but if our data is like we know the parameters, somehow we can transform to a normal distribution, then our test becomes like this, our test. Okay, so we will go and we'll see that. I'm going to quickly go to the R sessions, because then you will get more clarity what I am talking about in terms of interpreting the statistics. So we have in this lecture, we have t-tests basically covering and then we have the single sample, like we have a sample, one random variable which is having some values. We have a single sample, and we can do the single sample t-test. And we have two independent samples. That means we have two samples, but they are like there is no dependency between the samples. It's not like this data X and Y have any relationship, like X column data, Y column data. But we try to see if that is any like what is there. Like basically two group. Okay, we are trying to get a significance testing between the two groups of data. But if the data are dependent, like for example, you want to measure an effect of some treatment. So before treatment and after treatment on the same patient or like the same experiment. So we have X and Y. In that case, the observations data that come from X column, which is dependent like as an after effect of X having some treatment, which is the Y result. That is the scenario for paired test. So we have we will see that test. And then we will have the ANOVA, and the ANOVA test is needed because if we have more than two groups, because t-test is good if we have two groups only, okay? But in many practical scenarios, we may have more than two groups. So in that case, we can bootstrap the t-test, but if we do the t-test, like taking in each individual two groups as a one pair, and do that and look at the combination. If we have like a 15 groups to 2 to the power 15, like how many groups you can, how many combination you can have. So then it will be like a very exhaustive, and also we will run into the problem of making type on error because of the simple assumptions. So that's why t-test is not good for multi-group, and that's why we need ANOVA, which is a different kind of test, but it is not a test of the mean. It is causing the variance, like we have multiple groups, and what are the variance between this group. Okay, does the group vary or not? So that is the question we will try to answer through that, and that is hypothesis testing we do in the variance. Like, does the group has a variance or not? If not, then what is their variance? Like, which group has an impact over others? That kind of result we can get usually from the ANOVA. And for ANOVA, it is, since it is like a not like it's more than two groups, it's not a T distribution or a normal distribution, it's a F distribution. And F distribution is basically a kind of a distribution of variance. It's basically, it gives us like because other distribution of mean, but F distribution is distribution of variance. So it's like a ratio of the variance of groups. So unlike the other Z and T distribution, F distribution give us a variance. That's why there is no negative value of F distribution. It's just all positive value. Okay. And the result is F test, like Z test, T test, we get the F test, which gives us a kind of testing of equality of variance, and it tests the hypothesis of the equality of two population variances. Okay, and we'll see that, and if we see that there is differences, then there is further test to see which group has more, which group varies from other group. That test is called post hoc test. So post hoc test is required to identify if you reject the null hypothesis, and if you say no, I accept the alternative hypothesis, that means there are variations within the group, and now post hoc test will tell us which group has a variance comparing to other. Okay, let's see in the code session. Yes, categorical. That's basically, we will do it in the next week, okay? Because in this case, we all are numerical and continuous data we're talking about, but categorical data we'll do it in next week, which is our like Wilcoxon test or like a chi-square test. These are the non-parametric tests. Okay, so how to know what is the most appropriate type of test to choose? Okay, this is the whole point of discussion of this. So the first is, we are if you look at our lesson plan, we are doing parametric test. Okay, that means we know the parameter, which is either mean or variance. So if we can identify the mean and variance of the sample, like the formula how to calculate mean and variance, if we know that, then we will be able, we are good to do some kind of like a test like this, either t-test or variance test, or z-score or z-test. So if, and knowing of our sample size, we will see we should do a t-test or a z-test. If our sample is too big, big enough, then we can say the data could come from a normal distribution, so we can do a normal statistical test. If a sample is a small, then definitely we'll go for the t-test. And obviously this is a like a continuous and numerical data. But if we have a categorical data, like the categorical data, and we have a sense of order, then we got a sign test, a rank test. And if we have a other category, if you don't have order, then we can have a different test, which is non-parametric test, because we cannot calculate the mean or variance of those values. So we will do different tests, which is our next week lectures. Okay. Okay, yes. I think I have to take your seek your permission to carry on, because we have a lot of things on the art session. So probably you would mind if I go a bit longer, but definitely I will hand over the code to you so that you can run. And obviously you have your yes, I should share the screen first, and then just enter a screen. Good, thank you. Thanks for your confirmation. Yes, enter screen, and just we will quickly go to enter screen. List of sharing. Should like to share. Okay, what's that share? Okay. So, okay, good. So I think you can see my screen now. Okay, so okay, this. First, I will explain the topic confidence interval. Okay. So in this case, we have like R has inbuilt data called air quality. So we got air quality data, which is a data frame loaded 153 items. Okay, and then we are taking a random sample. So SRS is a simple random sample, and the function I'm using is sample to get 100 samples from this data. So if I run this, you will see that we will get 100 samples in SRS. I just open it. Now you can notice the index 11485. So look at the index 114, and if I rerun, and if I open it, you can see the sample, the different index is changed. That means it took a different random sample. That means the sample function is really giving us a simple random sample. So simple random sample is picked up through this function. Now we want to calculate the confidence interval is calculating or guessing the population. This is our population. Whole data was 153, and we have taken 100 samples, and we want to guess the mean of this population through a confidence interval. So now let's see. So this is just for curiosity. We know this is our we want to calculate the mean for the wind, because it has multiple variables the sample has. You can see we have the ozone data, we have the solar, we have wind temperature, but our column of interest in this case is wind speed across different time of the year. So we see the wind. So taking the wind, and we have taken the sample of the wind, and we want to calculate the mean of the wind. So this is our mu, which is our population mean, and you can see our population mean in this case is 9.95. Okay, but our sample mean is, now you see, sample mean is 9.65 we got. Okay, now we want to do, so imagine we don't know this, we don't know the whole population, we got the random sample like this. Okay, now we want to guess the population mean with different confidence. So this is our confidence levels. As a loop, I just want to say we have 90% confidence, 95% confidence, and 99% confidence, because you will see that the confidence level, if they increases, then our range also increases. Like if the confidence, yeah, it's just, if you are more confident, that means your range is bigger. If you're less confident, the range is small. Okay, so we'll see that population. So we just print that. This is our 9.95. And we have a confidence level, and we just for looping through that for each, and we see that. So I'll explain the code. So I run it. So for each confidence level, I'm taking the Q, that means there's the T statistics. from the distribution. I just showed you the distribution. So we are getting the t-value, and then t-value is multiplied, which is our z-value in this case, because this z and t-value is same value in this case. And then standard error is calculated using that same formula. It's all about on the sample. And then we are, like you said, upper limit and lower limit, because you saw the formula has a plus and minus. That means you have upper limit and the lower limit. So you have the lower limit in this case and upper limit. And now we print it out. And let's see what has been printed out. So it is showing the first Z score or the T score is, when we are 90% confident, is 1.66. And 1.66 level of confidence, the probability wise, that's the value we got. And then our range is 9.10 to 10. Look, 9.10, but our true mean is lying as 9. What is our true mean? In this case, like I have shown that, 9.95, which is our 9.95. So 9.90 to 10. So that means it lies between that. So from the central limit theorem, the sample is actually as a normal sample, and we are somehow safely, we can tell that from the 90% confidence level that our true mean is lying between these two. If we get 95% confidence, you see our range has increased from 8.9 to 10, like 10.31. We have previous 10.21. But if we get more confidence, if you say, no, I'm 99% sure that our sample mean will definitely fall between this, then your range has wider. Like, see, the more confidence you are, the ranges increases, like the confidence level. Okay, from 8.78 to 10. Definitely the mean falls between these two. So this is the idea of confidence interval. Given a sample, we can given a confidence level, you can tell the sample you can give a range of an estimate. Let me have a quick look what's happening there. Oh, the chat here. No, actually, it's basically up to the statistician how you interpret that. It's basically, if you want to be make 99% sure of estimating, there is no hard and fast rule that you have to be like always 99%. It's basically how you interpret, how much confidence level you want to give. Okay, there is no hard and fast rule of having a confidence level. Now, quickly, I will show you some techniques of detecting outliers, because as I see, the key factor of t-test is you have to have removed the outlier from the data. So there could be different kind of situation of detecting outlier. So if they're univariate, means if there is only one variable and you want to detect the outlier from that one variable, okay, that means one data set. So the example is straightforward. We just load the card data and we box plot the card data. As you can see, there is no outlier. Okay. Now I deliberately added some outlier in this case, because you can see 25 is our maximum. I have 5. So if I add 40, 60, definitely it is way above the. And if we replot the box plot, definitely you will get the effect on outlier. So I dropped these 4 outliers. I just added some like extra values, and now if we put the stats, we can see the function. Look at the function boxplot.stat. Okay, it gives you some interesting statistics. So it gives you out means outlier. Okay, if you say out, it will give you the outlier on the data. That means it is indicating 40, 60, 50, and 45 are the outliers on the data, which is exactly the same values I have added. So if you have this on a data, you don't need to add, because just for example, I just added to check. But now eventually, if you found this outlier through the graph and through this function out, how you can remove that outlier. Okay, this is the way you can remove the outlier. The function is outlier. I will explain here. So this is the, because you see the box plot stats and out. This give us the outliers, right? This is the whole set, like in this case, the out 40, 60. This is our values, okay? And now we can iterate through all of the cards, the data, okay? And then not take that from this array. That becomes our data, clean data set, right? So I'm looping like is a kind of a data wrangling. So we am taking all the car speed data, they are not within this the set or the vector, okay, and then they are in here. So if I do that again, it will get the plain simple data. So this is data without outlier. We'll get that data which is not coming, which are not this, okay. And eventually, if I print that, this is the same expression I have just to put you there. And if you say outlier here, then you can see the outliers, because this value is already got the outliers. So you can also do different data wrangling stuff. Like this is the simplest way you can get the outlier from this remove the outlier from one. So in the case of bivariate, like if you have multiple variables, at least two variables in this case, you can do this way. I'll just be quick. So we have one data set, and then I'm adding extra outliers because I know the data. So that's I have this. So I'm adding the two like a extra values, speed and distance. It becomes the two like a bivariate outlier. So I have car data car one, which is our original, and I have this outlier which I'm going to add or mix on the same data, which is our bind function, and same car one data plus this one. So I'm car two is having the data with outlier, okay. And see if I plot the data, okay, you can see there are obviously some outlier here. With an, if I put an AB line, you can see that. Oh, sorry. I should run this. Just you can see these. This is our like a best line of curve, fitting line. And then if I plot the original one without outlier, that means there is no outlier. Okay. Okay. So now it means I was successful to add some outlier on the car2 data. Okay. So and this is the plot. The box plot is the way you can see that data, and you can remove that data by their index. So now you can see this is the outlier, and I just like you can see this is the different outliers, and I use the cut function as well to see a smaller version of the outlier data. So I'll leave the code with you. You can run, and you can you can explain yourself. But if it is a bivariate case, the box plot, through visual way, you can do you can see that outlier, and you can remove the outlier from the data index. And in the case of multivariate, it's more than two variables. We have a function called cook distance, which is not in a lecture sheet, but it's good to know that. And you can research further. For example, in the case of we have the win versus the rest of the data. I plot that quickly. You will see that this is like a multiple data set, like win and rest of the other variables. And if I plot, so this red indicates the outlier, and the decision logic is 2 times means of cook distance. Like you can play like if it is 3 times means, then this is up to you what you want to declare as an outlier from the group of the data. Okay, so the key point is cook distance is giving us an outlier notion from a multivariate sense. Okay, but in the case we are handling only simple 1 or 2 cases, like a 2 sample data, so probably you're not worried, but this is just for your knowledge. You can do that. Okay, now we will do the t-test in terms of a parametric test. First is our sample test. So look at our interesting data set. So we walk you through the example for all the tests to the same example, same data set, which is like a startup data for Australian company. So we just load the data, which is the data set, and get to know like this is the data set from 50 Australian startup companies regarding their R&D expense, their administration expenses, and marketing expenses, and then where they belong to, where the startups are, and then their profit at the end of the year. Okay, so this is the data set we have, and we try to do some hypothesis testing on the interesting variables. Okay, so first we want to test what? First, our test is there is no significance difference between the sample mean and the test value, which is we will be testing like a 20K, 300K, or 200K as the mean value of sample mean of what marketing expenses. Okay, so because we saw that there are companies and we want to see whether there are any significant differences between their marketing expenses. Okay, marketing and it should be like more than 200 or less than 200. So we want to test that hypothesis. Okay, we said the marketing expense should not be get above or below that. So we are saying it's exactly, if our null hypothesis exactly mu is to 200k, and we want to check whether it is true or false. The null hypothesis is true or false. That means if it is false, that means we can take either like a one-sided, left-sided test. If it is like a want to say more than 200, if it is less than 200, then it's a left-sided test. If you said not equals to 200k, then it is like a two-sided test. Okay. So now we just run it, and then first we assume that it's a box plot, like data is normal for our marketing expenses across all the states of data. We are not biasing any state, so it's just all marketing expenses. And then also check the normality. So you can see the data is normal. I can say it fits in a line, so there is no anomaly in the data, and probably there is no outlier from the box plot. So we are good to go, and our null hypothesis is exactly 200k, and with a confidence level. And we run that test like a t-test, and then yeah, we can print this. The test result is printed, which is giving us the p-value is 0.1662. It is higher or less than 0.0 their confidence level. Okay, like our confidence level, no, our is the 0.05. Okay, this is our significance level. Okay, this is our significance level. So it is higher than that level, and you can plot that data like this, attributes with just attributes, and then okay, and then I think I need to load these two libraries to give you a nice graphical rejection region, which is this. And if I plot the test statistics, plot of result, you can see this is our rejection region because I did the two tests, because it's not exactly, so that means we cannot reject the null hypothesis because it is falling on the dot. So it's beyond, not beyond, it is not within the rejection region. It is within the probability curve. That means there is a good probability that the mu is equals to 200. Okay, so it's not like a not equals to, not or greater than or less than, so we cannot conclude that. Okay, so the mu is exactly like we, in this case our hypothesis, alternative hypothesis cannot be accepted. So now we do the two independent tests, two independent samples. In this case, we are biasing the sample in a way. We take the samples, either the state is Melbourne or Sydney, and we are trying to get the data from the where the state is like a Melbourne, the same data R&D spend. So we want to compare, because it's the R&D spend is not dependent. Okay, so we are getting the R&D spend expenditure from Melbourne companies and R&D expenditure from Sydney companies. So we are getting these two data set, which is the R&D Melbourne R&D and Sydney R&D, and this is how we can get the data. So this is like a subset function, subset, and this is our data set, the whole data set. Okay, where data set is this. We are setting only the profit. These are the three things we are selecting. So if you say the data test, and then data test is becoming like this. So we have state, profit, and select. But eventually, if you don't need to do that, you can take all the columns and then you can get the data like from the data frame where state equals to this. So this is also doable. But I'm just giving an early because you'll be learning R in the throughout journey. So this is why not you learn something in advance. So select will give us the specific columns to select, and you get those columns in the data set. And also you are only getting the data only for Melbourne and Sydney, which is your data set now. And from this data set, you are getting the subset of data, which is basically getting the Sydney and Melbourne. And this is your data set. And now that becomes our two independent samples. Okay, So these are our two independent samples now, and we want to check whether these data are null. So there is a test that give us a kind of a normality score. So Sapiro test, if you just Google and remember the name Sapiro test, which tells whether the data is normal. So we take the R&D expense from the Melbourne, whether it is normal. So you can say p-value is 0.7, which is very big than 0.05, like our significance level. That means we reject the null hypothesis and accept the alternative hypothesis. That means data is normal because we are testing the normality. So in this case, our alternative hypothesis is data is not normal, and our zero hypothesis is data is not normal. Alternative hypothesis is data is normal. So we are accepting null hypothesis, rejecting null hypothesis, and accepting the alternative. So that means data is normal. In this case, yes, it's also 0.22 bigger. So data is normal. So it is good for our t-test. So we just confirm that with the Sapiro test. Okay, but eventually you can do box plot like as I have done in the visual way. The same thing, probably your lecture note shows the visual way of box plotting, and also yeah, our QQ plot. So just a QQ normal line, and he said the data is fitting the lines. That means it's quite normal. So this is another way. Instead of box plotting, you can do Sapiro test, which is like another significance test of normality. Instead of eyeballing the data, this is like a statistical test to check normality. And also box plot, why not? Like by the state. So we have two states, and we can see the data. Now, as I said, our hypothesis is there is no difference, because we want to make the hypothesis that there is differences between Sydney and Melbourne in terms of the R&D expenses. Okay, that is our hypothesis. That means our research questions, which is our hypothesis. But now hypothesis then become, we'll know there is no difference in the mean R&D expenses between Melbourne and Sydney based their startups. Okay, so these are the like null hypothesis, and see if we can test that. So the formula t dot test, and this is the like a way in the R way of doing the test, two independent sample test, and we can print the statistics, and we can plot the statistics the same way we did that. Still, we cannot reject the null hypothesis. That means that we can say there is no difference between the R&D expense. Okay, but because it doesn't fall in the rejection region, it is falling here. So from the given data set and sample, we cannot reject the null hypothesis. Now we see if we do something like now if you say Melbourne and then profit. Let's try the same in another way. So we have another data set. We have the same data set like Sydney, Melbourne, because we try to prove this in a yeah, the other way of doing which is because the t dot test we also did here t dot test with the equation way. Because if you look at the t dot test formula, there are two ways we can pass this t test. This is a variable, and the tilde another variable. This is a kind of equation way. Other way we can pass x variable and y variable, and then confidence level, and then the variance of equality is true and alternative hypothesis is greater. Okay, so we have to check whether it's a greater, or you can say less, or like a two-tail. So in this case, we can do that. So we are just trying and see if this is the true for either of the way. Okay. So in the first test way, we found we cannot reject the null hypothesis. Now we do the second way. So load the data, and also checking the box plot, and then putting the box plot to check the normality. So this is the normal of Sydney and Melbourne. That means there is no outlier, so we don't need to remove an outlier. Now the way we can do the t-test, and with the t-test, and we see the value, the p-value is 0.387 in this case. Previously, what was the value we got? Is 0.387, and previously we got, in this case, 0.77. Okay, the formula gave us 0.77. That means it is bigger than 0.05. So we cannot, yes, so we cannot reject the null hypothesis. So we accept it, okay, because of higher value. Now we do the paired. So in this case, we think, look, the profit is actually dependent on some expenses, right? Because if you have more investment on R&D or marketing, then probably you can have a higher profit because you just make your good product. So that would be a dependency between your expenses and profit. And another way you can say these all are your like a input and predictor, and the profit is your like a dependent variable. It's an output. Okay, so that means there is some dependency. So in that case, we try to do the paired sample test, like because our pair is like a paired with profit is paired with marketing spend, and profit is paired with R&D spend. So we want to test both way, like just R&D like a marketing expense and marketing budget helps to earn more profit, or R&D spend helps to earn more profit. Okay, we try to formulate this hypothesis testing, like which one really helps to get profit. So first of all, then first, that's why we tried. First, we see the data nature, the R&D expense box plot. You see, there is no outlier in this case. Second one, so there is no major outlier, so we are good to go. And then plot this, okay, marketing and profit. That means there could be some relationship because it's on a scatter plot, marketing spend and profit. So there could be some like a linear or some kind of relationship probably we can ask. So we want to like instead of eyeballing on from the visual, we want to measure it whether there is really any relationship or not, because we're trying to do some then we can also the R&D spend and profit same way, and we try to do a line. So there could be some relationship. Okay, oh sorry, line should go, and there could be some, and we want to measure it basically from a statistical point of view, not in like a graphical. So first of all, our hypothesis in this case, there is no significant difference between R&D spend and profit. Okay, because we are trying to first R&D yeah. So because it seems that there could be relationship because of this linearity of spend and versus the profit. So we want to see like whether there is. Okay, so that's why our null hypothesis is there is no significant relationship or any difference between this. Okay, R&D versus profit, but there is differences. So now in this case, our standard is like we should, the baseline is mu0, and then we pass the two samples, like a sample is spend, marketing spend in the first case, and the second case we will say R&D spend and then profit. Okay, so first do the first test and see what does it say. It says okay, so where it is false, you see it's a rejection here in this case. That means it is telling that although from the visual we are not 100% clear about this line whether the relationship is obvious, but the probabilistic, the hypothesis testing is tell us no, there is significant relationship because it is you can see here. That means we are rejecting null hypothesis and we are accepting alternative hypothesis, which is there is significant relationship or there is differences in terms of realization of profit and marketing expenses. And let's see the second one. And let's see the print, and still it is falling the in the rejection region. That means we are rejecting the null hypothesis and accepting the alternative hypothesis. That means there is significant differences between these two. Okay, the R&D expense and profit. So this, from this like inferential statistic, we conclude that yes, the profit is actually dependent or has some effect on those two things. And eventually, when you in your last lecture, when you will do the regression analysis, you will see if you have a lot of variables, you see which variables impacting to get depend like the resultant, which is our in this case like your like dependent variable or is having an effect of these independent variables. Okay, these are the independent variables: marketing and then profit, and sorry, marketing, the R&D expense are independent variables, and dependent is profit. So which is having a like relationship within this and in this case, we are hypothesis testing is tell us probably these two is having some differences. That means they are significantly affecting each other. So now we will go to the ANOVA test. It is using yours like a lecture note example. So I'm just to making you assured that this is not a new data set. It is the same data set and same steps explained in your lecture note. So I just run it again and explain. So I just load the data. So there are many ways you can do ANOVA. So there are a couple of ways. This is just the manual way, which is a manually calculating the means of different groups, and then the variance of different groups, SSG and SSE, and then putting into the formula and finding the F star value or F value from the F distribution, and then from the rejection region, you can reject or accept. So this is the one way, which is basically the step-by-step and the theoretical way of doing it. But R has made our life easier. So instead of doing all these steps, which is exactly from your lecture note, we can see that, but like this. But one question you may have, like how we know that the 39 is the outlier? How can we know that, right? So to answer that, if you see how we remove the outlier. So if we load this data, as I have run that already, so now if I box plot this data, you can see data is normal. So I have to run this because otherwise it will not be. So the power function is giving is a kind of a like a multiple graphics in one row and column. So you can run it and then box plot. Did I run it? Visual inspection of the data, and then what is that? I just clear this. I think I didn't run this data. Okay, run this, and then oh, where is my plots? Oh, box plots. No, it's not plotting. It's strange. Oh, probably just clear everything from the environment and reload this data and do it again. vtemp. What is that? Error in names vtemp. Something wrong. Refresh it. Let's refresh that. Oh, I think something happened here. Some code is not. It's expecting some value here. Refresh that. Oh, sorry. What's that? Let me check. Escape. I did that escape because it's expecting it has got some extra character somewhere. So, oh yes. Oh, then I load the data. Yep. And then thanks. Yeah. Now it should give us all the graph. So it's showing us the normality of different variables, like different groups, like A, B, C, D. These are the different insecticides. And look at this data set because this probably give you some insight of your experimental design. So in this case, there are like the data set. If you see that, if you look at the metadata or the information of the data, it's just some insecticides has been applied, like 6 insecticides has been applied to a field, and it counted the number of insects after each. And that the count is giving us a number of insects, and we are trying to make an effect, like is there any effect on the number of insects presence after applying the insecticide, like which insecticide works better or is there any differences of having insecticides within this, like applying these insecticides, or A has a better impact over B, or B has better on C, or like is there any A, B, C same or not, or like this kind of a statistic, or this kind of test we want to make through this, or a conclusion we want to make. So this is the visual inspection, like data is normal. That means our assumption of normality is okay. And also you can do this test of like a bar strip chart and bar chart. So you can see this. You can see in the D the outlier. Okay, so that means in the D the value is the y-axis is showing is the value, which is the D in this case is probably above 10, between 10 to 15. So we want to eyeball the value between 10 to 15 for D. So what is our data set? Is data set is insect this. So if you see the value in D, A, B, C is sorted by spread quality. So D between 12 is the value, because you see there is only one value between 10 to 12. 10 to 15 is 12, and the index is 39. This is how we know that the value is 39. That should be removed as an outlier. Okay. So as you see, there is because in the lecture note you have to removing the outlier, because from there you found that, and this is how we know this is the 39, and you remove the 39 and outlier, and you rerun the box plot. And also you do transform this value to a square root instead of the normal count, so that it looks like in a scalar, because there is a kind of dispersion. But if you square root that and then you do the same box plot, or it is not the QQ plot again, and you can see they are still fit the normality, and then also the box plot and the jitter plot, you get the values are like closely each other. It's not very much dispersed, like it's a scale down to 15 because it's just square root. Okay, so it get a later square value. So this is basically when you can take the raw value, and eventually in a reduction note they said instead of taking the square root, take the exact count and run the statistics, you'll get the same result. But just for visual and for this kind of scaling, you did a square root value. Okay, so just this is the way I was showing, like you can do the method one, which is exactly your theory says. You put the SSG and SSE, and then you run the FS statistics and get the score, and we run it, and then from the FS star we can we get the statistical like FS star value, and from FS star we know the statistics, and from the function, like as I said, like a PF is the probability density function for F distribution, like a probability distribution for T function, a probability distribution normal function. We know that, so like PF is that function, and knowing these statistics and over statistics, and get the probability of the tail. So, and this is the probability we get, and we can say this probability is like this. That means it's very, very smaller. That means we can reject the null hypothesis and accept the alternative hypothesis. So what was our null hypothesis in this case? Okay, our null hypothesis was there is no differences between the mean, not the means, between the variances of those groups, number of insecticide, number of insect. Because remember, in our experimental design, what we are counting the number of insects after applying the insecticides. So, and our null hypothesis is there is the number is equal. There is no variance in the number of the insects found after applying the insecticides. This is a null hypothesis. The alternative hypothesis is there is. That means there is at least one group has less number of insects, or that means is ineffective on the insects. Okay, so that is our research question. So that, but since the p-value is very, very low, in this case we got like a 2.4 10 to the power minus 20. That means we are safe to reject the null hypothesis and accept the alternative hypothesis. So if that is the case, and we can prove that same hypothesis, the same value in different method, like one-way test, which has give us the, yeah, you can see the p-value is this. And also we can do another like a AOV function. So one-way ANOVA test, which is the R function. Again, AOV is the another R function, which takes the function as a parameter. Like you can see the equation, the square the square root of the count and the spray, which is our groups. Okay, and this is our data set, and we can run this again, and this will give us the same statistics. You can see the statistics spray wise, and then you can see the PF. The probability is still 3 star means is very low. That means significant. Okay, and on this level, so we can reject. So all 3 cases is giving us like a good rejection, a good ground for rejection of the null hypothesis. Now we have to do post hoc test. That means we want to see which group has a better effect, or is there anything we can make out of it. So to do that, we apply the pairwise t-test. Okay, and so we just do that. So we get, because the t-test is not actually the test of the variance. Okay, it test of the means. That's why we need to calculate the means of the data. So t-test is always after the mean. It considers the values of the mean. And we are now considering the pairwise t-test, like pairwise mean of those groups. So we are considering still again the square root of count and the each individual spray, and the t apply is a kind of is an R function, which is a kind of a bulk application of the function, which is this function is the mean. We are applying the mean, like calculating the mean of each group's data on this square count. That means we are counting the mean score for the spray 1, spray A, spray B, and spray C, and this is the ultimately giving us the result is ultimately giving us a kind of a vector. So if we run that, you will see the mean score. So this is the mean for A, mean for B, mean for C, mean for D, E, and F. That is basically our input in this case. Okay, and we are using an adjustment method. So if you Google, there are different adjustment method to meet the statistics, because we are doing pairwise t-test, but the most appropriate or most widely used is Bonferroni approach. So if you do that, it will give us a kind of explanation about different groups. So that is showing group A like 1, or at least like significant. Okay, like A, B is 1, A, F. That means we can say A, B, and F, they work similarly. Okay, they have because first we have already proven that there is differences. So now A, B, and F, they are like significantly, or they are different than other group. Is there any other grouping we can make? Like a C, there's a positive number here, 0.4. So C and E could be like working in a similar way. And from the visual, you can also see that, look at the graph, the box plot, like A, B, and F, they are having like a similarity, because they look at their box plot give us, because this is representing the number of insects. Okay, so they work similarly in terms of number of insects found after applying the insecticide. So this statistics is also showing us, giving us like A, B, and F could be in one group, and then C and A is one group, C and E could be one group, but there is no big like a value. It's not exactly one, but we got another one like E, D, and E. Again, D and E could be one group. So this is the way we can interpret the result, because we can say these groups are like making a group, and these are the differences they are making. So yeah, hopefully this is basically, and also there is another method, which is the like linear regression method, which will know when you do the linear regression and do the analysis. So it is actually giving us the same result as well, in terms of the probability. Okay, you can see the factor, and the probability is like very less. This is the exact equation we do linear regression, but no need to like do this now. But all the methods we try to like point that to test the ANOVA. analysis of variance, and if we get the hypothesis 0 false, then we do the post hoc test, which is our pairwise t-test on the mean, and then we can see the from the result we can see the grouping, and that then we can interpret. Okay, and your lecture note has some, and I also have some from the same data set. You can run it by yourself. I'm not going to take much of your time now. So it is like it's a profit and a state. We want to see the dependency in term, because we have 3 estates in this case: Melbourne, Sydney, and Adelaide. And then the profit, we want to see is there any differences in the in terms of realization of profit of the startup companies, and we are doing the ANOVA testing. Okay, so I just leave it with you, and you can see this. So I just run it, and then you can interpret it as an exam, as your exercise. Or data set is missing because I refreshed the, so I have to reload the data set. In this case, where is the data set? Probably not that one. The data set here. So I just load the data set, and now if I just go at the very bottom, and now I just refresh everything here, graph, and then strip chart to give us the normality. The data is very much normal across the 3 states, and we can see if any, yeah, and then we can see you can see Melbourne and Sydney, Melbourne and Adelaide could be so Melbourne and Sydney is not very much. That means what is our T statistics is showing 0.5. Okay, so we cannot reject we cannot reject our null hypothesis. So that means there is no difference. So probably in a startup company, we can say probably there is no, because wherever you are located, profit doesn't impact. So this is the data set is showing. Okay. So yeah, because of oh no, it is basically rejecting the hypothesis because it's no, is above 0.5. Yeah, it's not less. Yeah, so we cannot reject the null hypothesis. We accept the null hypothesis. That means there is no differences in this case. Okay, so yeah, that's the end of this lecture. And so I think your next is coming of some non-parametric test. And then once you know both end of the statistical tests and the sample result, the sample statistics and the sample you will be collecting from your data, and then you will report on your capstone using the sum of the tests to test some of the hypotheses of your sample data and interpret the result. So I just stop sharing this, and I will upload the slide, and you have a wonderful week. And thank you again. Okay, just stop the recording.